Hello, welcome back to the continuation of differentiation. This is video number 5, and in this video we want to look at how to differentiate simple trigonometric functions. We know we have 3 trig ratios, and then we have other 3 ratios that are derived from the first fundamental 3 ratios, and so we want to learn how to differentiate them. Based on the syllabus, we are not supposed to do detailed work. We are supposed to just look at how to differentiate the simple trig functions. And the first one is, if I differentiate, or if you differentiate sine x, you get cos x. So sine x will give you cos x. If you differentiate cos x, you get negative sine x. If you differentiate tan x, you get sec square x. Remember, sec is part of the derived ratios. It means 1 over cos will give you sec. And so when you differentiate tan x, you get sec square x. Again, if you differentiate cot s, which is the same as 1 over tan x, you get negative cosec square x. And remember that cosec also is the same as 1 over sine x. If you differentiate sec x, the result will be sec s tan x. And finally, if you differentiate cosec s, you get negative cosec x cot x. We'll prove that of one of the ratios of maybe sine s or cos s to see whether really it is true. We use the first principle to differentiate sine s to see whether we get cos x. I'll do only one, then you use the one that I will do as a form of example to do the rest if you wish to do that. But before we do that, there are some principles we need to take note of. And this will help us to do the proof. That's why I'm bringing it across. If you've done limit, this is part of the things you study under limit. Maybe search for the video under limit, and that will help you understand better. If you take the limit as a approaches 0 of cos s, you always get the same as cos x. The reason being that since cos s has no a, it means that if you take a approaching 0, there wouldn't be any value of a to substitute, and so the value will be the same. And so cos x will be the same as cos s if you take the limit as a approaches 0. But then if you take the limit as s approaches 0 of cos s, you get 1. Here the assumption is that when you substitute 0 in place of x, cos 0 is 1. Right, that is what happens. But it doesn't work always. You have to substitute. Sometimes you have to simplify before you substitute. But it's just, I want you to just take note of. And the limit you will understand better. Now, if you take the limit as s approaches 0 of sine x, that also gives you 0. Then another one I want to take note of is when you take the limit as s approaches 0 of sine x on x. Here, if you substitute 0, 0, it will give you undefined. But we don't cancel as well, but we have to simplify and we'll get 1. And the limit, you will understand that one. The limit as s approaches 0 of cos s minus 1 equals 0. That is when you divide it by x. And finally, if you take the limit as s approaches 1 of tan s, will give you infinity. Now, if you want to prove all the trig ratios, how their differential gives you the corresponding answers that we had earlier, at a point in time, you will need these particular theorems to get your final answers. That is why I've given them to you. But I'll be using only one of them to prove what we are supposed to learn. We want to prove this particular principle of saying that if you differentiate, and we know that in simple terms, differentiating sine s will give you cos x. But we want to use the first principle to prove that if you differentiate sine x, you always get cos x. And what I'm going to teach you, you can use the same thing to differentiate the cos to get a negative sine x, and that of the tan to give you the sec square x as we saw earlier. And so we want to use the first principle approach in doing this. And by first principle, if you have dy dx is equals to the limit as h approaches 0 of f of s plus h minus f of s, all divided by h. And so we can say that dy dx is equals to our limit, always write our limit, and then f of x plus h. It means our sign, whatever we see as, we put s plus h. That will give us sine into bracket s plus h minus f of s itself, which is the same as the sine x, all divided by h. And so this is what we have. Now I want to look at this aspect alone. Look at this aspect of the function. Sine s plus h is like writing sine using compound angle sine a b. If you remember how to expand sine a plus b, you can easily expand sine s plus h. So based on trigonometry, that is, if you've done trigonometry and you've done compound angles, you can see that sine a plus b will give you sine a cos b plus cos a sine b. That is, we are saying that sine a plus b, per the theorem that we know already from our trigonometric lesson, will give us sine a cos b plus sine b cos a. So when we substitute that into this function that we have here, it means to expand sine s plus h will be sine s plus sine x cos h plus sine h cos x, then minus x, all divided by h. Now we can rearrange this one by having limit as h approaches 0. Now we can keep our sine x cos h minus, that's bringing this one closer, x, then plus sine h cos x, all divided by h. I can then factor sine x out because I have sine s here, sine x here, so that I have cos h minus 1, then plus sine h cos x, all divided by, and even with that, all divided by, I can choose to make it this one alone divided by h and this one alone divided by h, which will mean the same, right? This same equation can be written as limit as h approaches 0. See that I'm repeating the limit because I've not taken limit yet. Can be written as sine x into bracket cos h minus 1 on h here plus sine h cos x, all divided by h. The same thing, I've not done anything new, just that at this part of the equation, instead of letting everything be over h, I just want to have the over h on the cos h minus 1. Actually, when I expand, I'll still get everything over h, so then there's nothing different here. Now what I want to do next is to take the limit of everything we have here. Remember, the limits affect everything here, and so we can think of taking the limit of x, that's sine x alone, the limit of cos h minus 1 on h alone, the limit of, now this one too can be split in the form of cos x then times sine h on h separately, like we did for this part of the work. And so when I take limit to each term that we have here, This will be the result. I want to have the typing version of it because writing it will be quite lengthy. And so this will be the outcome. So the outcome will be dy dx is equals the limit as h approaches 0 of this separately, the limit as h approaches 0 of the cos, that is this part of it, separately, then the limit of the cos x, that is this part, and then finally the limit of the sine h on h separately. And so we want to go back to what we studied earlier. I asked you to take note of some principles. Let me bring that one back again for you to see what it means to take the limit. We saw this earlier, that the limit of a, as a approaches 0 of cos x, will give us x, and the same thing applies to sine x. It means when I replace this one by sine x, I'll still get sine x here. And we'll also be applying this also, that is the limit as s approaches 0 of sine x on x is equals to 1. And so take note that we have something like sine h over h, the limit of it will be equals to 1. Then also take note of the fact that this part of the work here, the limit as s approaches 0 of cos x minus 1 over x will be 0. And remember, in our question we have cos h minus 1 over h, so that also is going to give us 0 here. And so we need this principle here plus this plus that and the sign of this part to help us solve or to finalize the question that we are dealing with. The proof that we are handling now. Now, if what we are saying is true, then if I take the limit of sine x as h approaches 0, because we don't have h in sine x here, it means that alone will give me sine x again, times the limit as h approaches 0 of cos h minus 1 over sine over h will be 0. We saw that. Then plus, take note of this limit alone, the limit as h approaches 0 of cos s will give us the same as cos x. Then times the limit as h approaches 0 of sine h on the same h will give us what? Guess? 1. Good. So if that is the case, then sine s times 0 is 0, plus cos s times 1 is same as cos x. And so 0 plus cos s will give us 0. And that is why we can conclude by saying that dy dx is equals to cos x, meaning that if you have y to be the function s, that's sine x, if you differentiate y with respect to s, you get y prime, that's the y differential, will give you cos x. Now, if I change this one in terms of cos, I can go through the same process and the result will be negative sine x. If I change this and use tan, I can go through the same process and I'll get the same answer. You have to bear in mind that you need some principle like the compound angle to handle this type of question. So that is the proof. In fact, you can go ahead and prove, but per our syllabus, we're not supposed to do a lot of proofs here. And so just knowing this will help you to understand what you are doing as far as trigonometry is concerned. Example number 1. So we want to apply what we've learned so far in solving general questions with trigonometry. So we want to find the derivative of cos x plus sine x. And so we know that cos s plus sine s more or less can be we can say y is equals to that. And so we want to differentiate with respect to x. So if I differentiate cos, I'll get negative sine x, plus if I differentiate sine, I'll get cos x. And so that is the result, as simple as that. So the derivative of cos s plus sine s is equal to negative sine s plus cos x. Example number 2. We want to differentiate 3 minus cos x. And for 3 minus cos s, if the function is y, which is equal to 3 minus cos x, then to differentiate y, this time let me use y prime to show the differential. If I differentiate 3, I'll get 0. Minus differentiating cos s will give me negative sine x. And so the result will be sine x, because this and this will give you a positive. And so the result for differentiation of 3 minus cos s is equals to sine x. Example number 3. At any point in time, you can try your hand by pausing the video, solve it yourself, and check the answer as I work out with you. Now with this one, we are differentiating y is equals to sine s cos 2x. And here we need to apply the principle that we learned already. I mean, chain rule, product rule, I mean, all those rules are applicable here. Whether the implicit function whatsoever, you can apply all of them here. And here we are multiplying sine s times cos 2x. And so to differentiate, y prime will be equal to, and because it's sine s multiplying cos s, we can use the product rule here. And so we hold the first one, we hold the sine x, then we differentiate cos 2x. And remember, cos 2x is a function of a function. It's cos as a general function and then 2s as another function. And so when I differentiate cos 2s, it will be negative sine 2x. Then I differentiate 2s separately, which will give me 2. Plus, this time I'm going to hold cos 2x and differentiate sine x, which will be cos x. And so when I rearrange this, I can write negative 2 sine s sine 2x plus cos s cos 2x. And so this is what will be the result. I mean, this is the result. And we can't add, we can't subtract. Sometimes you may be tempted to say that these two here can multiply the 2 here to give you 4. It doesn't work that way. And if not for the fact that this 2 also is here, we could have looked at this part of the work and then simplify it in the form of compound angle, which will be the same as sine cos into bracket a minus b, and that will simplify the whole of this to give you something like, if not for the 2 here, we could have simplified the work to be cos into bracket s plus 2x. I mean, in the compound form, this is what we could have written, but these two will make our answer to be just like that. Nothing should be done to it again. Now let's take another example and see. So example number 4, you can pause the video as well and try your hand on them. And then this will be the results. If we differentiate, so the dy dx is the same as y prime. And here, once again, I have product rule here. So I can hold the 5 cos. Oh, hold on. No, we can't use the product rule here. We need to apply rather the normal differential, which I will say y prime is equals to. Now, when I differentiate the whole of this, cos of this, we assume that it's like cos x. The whole of this function represents like x. So when I differentiate cos s, I have negative sine x, right? And so I'm going to say 5 sine into bracket 3x squared minus 4. Okay, and because within this also is a function, I can differentiate that as well. And so when I differentiate, I'll multiply by differentiating the interior function, which will be 6x. And so together, I'm going to have this 6 can multiply the negative 5 here to give me negative 30x sine into bracket 3x squared minus 4. And so that will be the result. I think that's very cool and simple. Again, let me go over again. 5 cos into bracket that. I'm differentiating that the 5 is a constant, so it will still remain 5. And if I differentiate cos, I get negative sign, so it will start with a negative 5 sign into bracket everything I have here. Then times differentiating what is inside the bracket, which will be sine x. 6x. And so when I multiply, then I get this. And that is application of chain rule. Okay. Before we move on to other or more examples, I want to take note of the following theorems also that will help us to do calculations. If you are given a function, let's say y is equals to sine ax, like we saw something like 2x sine 2x. If you differentiate sine ax, where a is a constant, it will give you the a out cos ax. Okay, that is what it means. Then again, if you have cos ax and you differentiate, you get negative a sine ax. Maybe I'll prove that one too for you to see how it works. So in general, when I give you y equals sine f of x, sine is a function and f of x is also a function. So to do a function of a function, you first differentiate the sine, which will give you the cos over here of the f of x. Then you differentiate the function f of x, which will give you f prime of x. So we've already used it, and I'm just trying to give you a theorem of it. So that is what it means. Then let's take the final one. If you have cos of a function f of x, and you differentiate cos at the same time of a function, like if I give you cos 2x squared or cos x squared, you differentiate the cos, which will give you negative sine s of the function, then times differentiate the function again, which will give you the f prime of the x sine f of x. So this is what I want you to take note of. Then again, I want you to also look at something here, how to differentiate powers of trigonometric functions. Some of the functions will come with powers, like I give you y is equals to cos nx. Let's say cos squared x. We'll take examples and we'll look at it. How do we get an answer for that? If you differentiate this, you get negative, differentiating cos will give you negative sign. And so the negative sign will be here. Then you differentiate within, and this will be the outcome. We'll prove that soon, and you see why the differential of cos nx will give us n cos n minus 1 x sine x. And the same thing, if it is sine, it also gives us this as a formula. You can keep it as a formula. Anytime you are given the function, just substitute that into the formula, and then you are done. But I will explain detailed so that in case you forget about this theorem, you can still do it on your own without any struggling. For the beginning part, we said that if you have y is equals to sine ax, then if you differentiate y, you get a cos ax. So what it means is that if I have y is equals to sine, let's say 3x, and I'm to differentiate this, it means when I differentiate the whole of sine 3x, I'll get cos 3x. And this is a function on its own, and so I will differentiate that function, which will give me 3. And so In nutshell, I'm going to get a 3 multiplying the whole of this as 3 cos 3x. And that is what the theorem is saying. I think that's very cool. Good. Now the second part too, we saw something like y equals cos x to the power cos n x. Then we see when we differentiate, this is what we get. Now what it means is that if I give you something like y is equals to cos squared x, it's more or less saying we are having cos x times cos x. That's what it means. If you've done trigonometry, this is very simple to express as that. And so when we want to differentiate cos x, and you use the product rule, it means you hold cos x and you differentiate cos x, which will be negative sine x. Then plus, you hold cos x again and differentiate cos x. It means I hold this one, I differentiate this one. Right. Then I hold this one this time around, which is cos x, and when I differentiate this one, it will still give me negative sine x. So what it means is that this will give me, it means I have negative, this part of the work will give me negative sine x cos x, then minus sine x cos x again. And so I can just write negative 2 sine x cos x. And that is what satisfies this theorem that we saw earlier, that the power n will come as negative, then 1 minus n minus that's the power minus 1 of x, then the sine x. And you can see the same thing here. The power is 2, and so it comes as negative 2 sine x, then cos x. And here it is 2 minus 1, which is the same as 1, so it won't come at all, so that we have this. So that's what it means. It means we can use the same principle to differentiate cos power 3 of x. And instead of having to expand it like we've done for this, we can just quote the formula straight away and substitute, which is going to be negative 3 cos power 2x sine x. That's what it means, as simple as that. So if you don't want to go through the stress, you can just keep the formula, and this will be the result when you differentiate cos power 3x. You get just that, right? Now let's look at one example here under the higher powers of trig. Now if I have y is equals to this function given, and I want to differentiate with respect to x, here I can use the product rule, because I have the power 2 means that it's a function within a function. And if I say let u be equals to cos into bracket x squared plus 4, in that case, then the whole y can be written as so 3u squared, right? Because I'm representing the whole of this by u, and that is squared. Remember that cos x all power 2 is the same as cos squared x. That's just that. And so cos squared x means cos x times cos x. So the whole of this means the whole of this times itself. So everything here times itself. That's why I can say u squared for that part of the function. You need to grab this concept here before we continue. So I want to write the y equals the u, that's 3u squared here. Now when I differentiate u with respect to x, now I'm going to differentiate. So when I differentiate u, I'm going to get negative sine into bracket x squared plus 4. Then I'll differentiate within, which is 2x. That's. Then here I can differentiate dy du also as 6u to the power 1. Then quoting the the product rule for that dy ds is equals to dy du times du ds. We've done this already, so you know that. So we are going to substitute dy dx. We'll substitute rather dy du first times du dx. So we have dy dx. We have dy du give us 6u times du ds is this part of the function, so we have negative. I can write it negative 2x because the 2x here, I can write it there, sine into bracket s squared plus 4 and close my bracket. Then doing back substitution, what is my u? The u originally we said is the same as cos, that's this one, s squared plus 4. So for back substitution, we can say this is 6 times cos s squared plus 4, then times negative 2x sine s squared plus 4. Now when I simplify this finally, I've moved so much. If I simplify this finally, you see this 2 here can multiply the 6 here. So that I have dy ds is going to be 2 times that will give me negative 12 of x, then into bracket cos s squared plus 4, then sine s squared plus 4. So this will be the final result for such differentiation of that trig function given. It's quite complicated, but if you take your time and understand the principles, you know your rules, your power rule, your chain rule, your product rule, implicit function, how to hold this and differentiate that, how to hold that and differentiate this. If all those principles are well taken, I believe solving these questions wouldn't be so much of a problem. And one thing I would like to advise you as a student is that these examples I've given you in this video wouldn't be enough to understand everything about differentiation in terms of trigonometry. You need to solve more questions. The more questions you solve, the better the understanding. So go ahead and solve series of questions on your own. There are a lot of questions in Aquila, in Approaches series, Akron. Past questions are flowing here and there. I mean, there are a lot of thousands of questions in there. Go ahead and grab copies and solve them, and I believe that will be of help to you. Let's take another example to help us understand what you've done so far. Now, let's take this as a second example under the higher powers or the powers of trigonometric function. Now, this one, using the product rule again, we can let u be equal to sine x. In that case, the whole of the function y can be written as u to the power 4 because of the power 4 here. Now, when I differentiate this part alone, that is the du dx, differentiating sine x will give me cos x. As simple as that. Then differentiating this one with respect to u will give me 4u to the power 3. Then based on our product rule, we can say that dy dx is equals to dy du, and dy du is 4u cubed times du ds, which is cos x. Now when I substitute the u back, then I will say 4 sine cube x cos x. This will be the result. Now if you go by the formula that I gave you earlier, you can use that one. If you memorize the formula, you can use that one straight away to get a differential function, because they won't specify whether to use the product rule or to use the formula work, or so they'll just say differentiate this, and that is what we have. So if we go by that formula work, it means that y given as sine to the power 4x will be equal to n sine n minus 1 s cos x. This is the formula that we saw earlier. So in view of that, if I want to substitute that straight away, I would say the 4 will be 4 sine, then I subtract 1, get 3 of x, then cos x will come straight away, and that is your result. And this is exactly what we solved as this. So what we have here is the same as what we had also over here. See, they are the same. Good. Now try the following questions on your own and see whether you can get the results as such. These are just ordinary trigonometric functions that you have to just simplify. Try your hand and then solve more other questions from other books that you can lay your hands on. And I believe this will be a very wonderful topic that you will really appreciate as far as differentiation is concerned. So we'll call this video number 5, and then we will go for the next video, or more or less to say that it will end the first part of differentiation. Our next video is going to be application of differentiation.